Okay, yeah, please, Friedrich, go ahead.
Thank you. So thanks everyone for coming, and thank you for giving me the opportunity to talk here about the work that I've been doing together with my former supervisor, Pavel Ševera. So this is a work with Pavel. And namely this one. So it's roughly called like the title. Yeah, so I assume you hear me well and you can see the cursor. If that's not the case, then please. Okay.
Yeah, no, it's good.
So the idea is to let me make do a small outline. So I want to so after some like introductory talk, I will talk about some structures that you can put on current algebroids, so such as generalized metrics. And divergences, divergence operators. So I assume perhaps most of you know these things, but I will still go through them. So hopefully that's not. If you feel that I'm too slow, then tell me. Or if you think that I'm too fast, then just I can adjust. Yeah, then I will talk about the generalized Ricci tensor, which I think has been also covered, but this will be from some different angle a little bit maybe. And then I will talk about the Laplace operator and the associate and the scalar curvature on current algebroids. So generalized scalar curvature. Oops. And finally, one more structure that you actually don't put, but that is canonically present on any current algebra is a generating Dirac operator. So I will explain what that is and what is the conceptual way to get it without requiring any choices or things like that. And then then perhaps next time I will talk about the application of this in supergravity or in like string theory in general. And that will be so on the side of current algebra, this will correspond to pullbacks and reductions. Pullbacks and reductions, which will physically correspond to Poisson-Litty duality, which is some sort of generalization of a T duality from string theory, and equivalent and reductions will be related to some sort of upgrade of that story, which in the literature it goes under the name dressing cosets. But probably it's okay. So far it's just a mysterious name, and I will come to it and explain how it relates to everything else. And then type 2 supergravities. So this thing will be related to especially this Dirac generating operator. And then I will finish with some examples. Okay, so yeah, that's the plan. Let's see how it goes. Yeah, so let me start explaining these notions. So let me start with the first one. So generalized metrics and the divergences. So I have maybe a question for the audience. So the question is if whether everyone is familiar with current algebroids or whether I should write down like I should
regardless of familiarity. I think write it down.
Okay, very good. Okay, so let me start with the thing that has to happen in every paper which deals with current algebroids, and that's the definition. So current algebroid. So everything here will be in the smooth settings, over real numbers, and all that. So this thing is given. So it consists of the following data. So there is a vector bundle. So this is a vector bundle, which is equipped with some structure. So first and foremost, there is a bracket on the space of sections. So this thing is an R-linear map on the space of sections. So you are supposed to imagine that this in some sense generalizes the Lie bracket on the Lie algebra. Then there is a non-degenerate symmetric bilinear form on the fibers. And finally, there is a map called the anchor map, which is so this thing is a vector bundle map from E to Tm. This is the anchor. So we have these 4 pieces of data, and then there is some axioms that this data is subject to. And so let me write them down. So such that. So most importantly, I mean, okay, perhaps most importantly, the bracket is a derivation of itself. So you can call this a Jacobi or Jacobi identity or Leibniz identity. So this thing is a derivation. Sorry, but yeah, but what I mean by this is that if you take a section A, so this thing is a derivation of the bracket, derivation of the bracket. Basically, okay, so let me still write it fully. So if I put bracket of B and C and then apply A, then this is the same as if I would attack with A on B plus attacking C. And then there is a condition which says that actually, so this bracket is not linear with respect to functions, only with respect to real numbers. So to quantify exactly what is happening, so suppose that I have 2 sections A and B, and I multiply the first one with the function, sorry, the second one with the function, then this thing is the same as if I would take it out, but there is another term where this A acts on F. And the only way it can possibly act on the function is via this anchor map. So I use the anchor map to map this section A into a section of Tm, therefore, in other words, a vector field, and then I take the derivative of F. So, okay. We also need to know how, I mean, okay, an important question also is that, like, what happens if I put a function in the first slot? But this will be answered in a second. Before that, let me also say that the action of that there is a compatibility between the bracket and the inner product. So you can say, in a fashion similar to the first one, you can say that the inner product is preserved by the action. So the action of A preserves the inner product. To write it down explicitly, what it means is that if you take a inner product of 2 sections B and C, and then you get a function, and then you apply a row of A, then this is the same as this thing. This one plus B bracket with C. So in all 3 terms, you are supposed to imagine this thing as like A acting on stuff. So A, in this case, A acts on another function via the bracket, and in this case, A acts on a function via the anchor map. So that's the analog of the first condition. And then finally, perhaps the strangest condition is that you have that the bracket is not required to be skew symmetric. So it's not the Lie bracket. But the symmetric part of it is given in terms of the inner product. That's some, okay. And more precisely, what this means is that you take the inner product of A and B, you get a function on the base manifold on M. So then you want to get a section of E. So the only thing you can do is that you apply the differential, you get a 1 form. So this is now a section of T star M. And now we can use the transpose of the anchor map. So that if rho goes in this direction, then the transpose will go from the dual to the dual. But the dual we can identify with E. So we will often use this trick that, like, because we have this sort of inner product, and we can always identify the duals of the fibers with themselves, with the fibers themselves. So in this case, yeah, if I apply the transpose of the anchor, I get mapped into here, but I can identify it with E, and yeah, that's it. And some people put 1/2, but, or sorry, 2, I guess, but I won't. Okay, so that's the end of the definition. And so the first consequence of this definition is that you can show that for every Courant algebroid there is a natural associated sequence, which goes as follows. We have used the transpose of the anchor to map it into, sorry, equal to Tm equal to 0. So basically, what I'm claiming here is that if you compose rho with followed by the transpose of rho, then this is 0. And this thing follows from the axiom. It's a fun exercise to show that, but yeah, let's not do it here. But like, so basically, what you can show from the first two axioms, you can show that these two guys imply that the anchor map is actually a bracket preserving operation. So if you take the bracket of two things, and then you take the anchor, and if you take the anchor and then you take the commutator of vector field, then this is the same thing. Now, and knowing this thing, if you apply this thing in the last axiom here, then the left-hand side vanishes after applying rho, and the right-hand side gives precisely this condition that rho followed by, sorry, rho transpose followed by rho gives 0. So yeah, and we say that, so when this sequence is actually exact, so if that sequence is exact, we say that the Courant algebra is exact. The Courant algebra, let me write here, is exact. This is a definition. Okay, and now a fundamental result sort of is a theorem due to Powell that exact Courant algebroids over some given base, over M, are classified by the third cohomology group of the manifold. And even more than that, like there is a specific correspondence. So let me explain that. So suppose now that I have an algebra which is exact. So if this is exact, then I get it. Yeah.
Can I ask a question? Maybe,
Yes,
maybe it's silly, but so from that last condition, I see that rho after rho transpose is 0, but only on exact forms.
Yes, but yeah, good point. But yeah, right. So we know that rho of rho transpose on exact stuff is 0. But the point is that this rho transpose followed by, sorry, rho transpose followed by rho. This is a vector bundle map, so you can treat it fiber-wise, like point-wise. And if you do it point-wise, then the
I see. Oh, I see. Okay.
Yeah, like every yeah, but it's that basically.
It's
like
linear,
the
right.
exact
Okay,
things span
cool.
the whole fiber.
Makes sense. Thanks.
Right. Yeah. So suppose that E is exact. Now, if it is exact, then you can show that you can always choose a splitting of this. So the sequence always splits in a way that claim is that you can always identify this thing with Tm plus T star M in a way that this Tm here is actually isotropic. So there always exists an isotropic splitting. You can prove that using, for instance, partition of unity or something. So meaning that like in this Tm, if you take two elements of that, then the inner product is 0. Yeah. And once you chose such a splitting, so suppose now that we have chosen such a splitting, then you can show that under this identification the axioms basically constrain the form of the thing. So they tell you that, for instance, the anchor map, if you take a section of this thing, so sections of this thing is the same as pairs of a vector field and one form. So right, so you can show that under this identification you will always have that the anchor map is just projection on the first factor, the inner product beta will be given by the only thing that you can imagine, and that's the pairing of these two things. So alpha on y plus beta on x. And most importantly, you can show that the bracket will have the following form, that the vector field part will be given by the commutator of these two vector fields, and the one form part will be given by this thing minus this thing. So here you can see that it's not skew symmetric. And then in general you can have some sort of three form, which is constrained to be closed, I think by maybe Jacobi or something, or by one of the axioms. So just to summarize, so if you have an exact Courant algebroid, then if you choose an isotropic splitting, you can show that the axiom basically they tell you that like the structures have to have this form, and the only freedom here is this H. And now what happens is that when you choose a different isotropic splitting, so this isotropic splitting, they are always related, they differ by a two form in a sense. And if you change an isotropic splitting, then basically this H will change. So you'll get a different H, but that one will be given by an exact piece. So you take, so this is the B that enters here. So basically it's because you have, if you have Tm and you have T star M, and if you now want to choose a different splitting, it means that you're choosing a different T star M. So this is really your like new T star, sorry, you're choosing different Tm. And this different Tm is also supposed to be isotropic. And now if you see it as a graph of a map from Tm to T star M, then isotropy means that it's skew symmetric, and hence that gives the B in here. So the upshot is that, yeah, that you can that it's only the cohomology class that is relevant. Yeah, so this is basically how the proof goes, and it's in a sense it will be. Mm-hmm.
Can you say something about the morphisms that you use for the classification?
Right. So yeah. So this is so what is meant here is that these are exact Courant algebras up to isomorphism, which I guess which projects to identity on the base. Is that what you were asking?
Yeah.
Right. Yeah. So yeah, I guess it might happen that you have. Right. Yeah. So here I really mean that if you have two exact Courant algebras, then they are equivalent if you can find the vector bundle map. Yeah, which gives an isomorphism.
Okay.
Thanks. Thank you. Okay. Right. So this formula, incidentally, so this gives the one of the most important classes of Courant algebroids, so these exact ones. So we know that they are locally always of this form. And yeah, and there is a different, very different type of Courant algebroids, which are given by the condition. So if you instead of focusing on exactness of the sequence, if you instead focus on the cases where the underlying manifold is just a point, so that's a very different direction in which you can go. Then the anchor map rho is trivial, and the only thing you have is a bracket and inner product. But since this D here is 0 because we are on a point. I mean, sorry, there is no d. So the bracket is actually skew symmetric, and hence you get the Lie algebra. So if this is a point, then courant algebra just corresponds to a Lie algebra with an invariant pairing, something which is called quadratic Lie algebra. So a good instance would be any semi-simple thing with a killing form. Okay, and now some more interesting things. So now some structures that you can put on this courant algebra is that one thing you can do is you can put an analog of a metric. So in this case, it will be called generalized metric. So let me say definition. So there is several ways how to think about it. So the one which will be useful in this approach is in terms of a subbundle. So we say the definition of generalized metric. On a courant algebroid. So there is a fix a courant algebroid, and the generalized metric is a subbundle. And let's call it V plus, for reasons that will be apparent in a moment. Subbundle such that if you restrict the inner product on that subbundle, then it becomes positive definite. And yeah, so this definition is a little bit negotiable. You can relax some assumptions. So you can also relax this. It's actually only necessary for it to be non-degenerate, depending on what you want to do with it. But the definition I will use is that we want that first of all this thing is positive definite, and that if you define V minus to be the complement, the orthogonal complement of V plus, then we want that there it's negative definite. So basically it's a maximally positive definite subbundle. I guess you can say it like that. Yeah, so there is various other definitions. Basically, some people say that it's an operator. It's some sort of automorphism. It's an operator that acts on the fibers of the bundle, and that operator would basically be in this language. This would be a reflection with it would be reflection with respect to this V plus. So that operator would be something that is identity on V plus and minus identity on V minus. A different way is that another different way that some people say that it's an inner product on the fibers, and that you get if you compose this reflection with the inner product, that with this bracket, with this inner product. But yeah, in any case, like it's definitely one good way of think about it is to use this definition that it's a subbundle. And yeah, and now the most important, an important observation is that if you have an exact courant algebroid, over some M plus a generalized metric, some plus some V plus, this is in one-to-one correspondence with a pair of a metric in a closed tree form. So on M. So this is a Riemannian metric. And this thing here is a closed tree form. But in this case, but now it's a specific closed tree form. It's not a cohomology class. It's really a concrete tree form. And the correspondence, and to show how this works, is just imagine that you start with an exact courant algebroid, and now similarly to this above discussion, just suppose that you pick a splitting. So you pick an isotropic splitting. Now if you do that, then you can at any given point on M, you can see E. Okay, let me pictorially split it into these two bits. So this is E at a given point, and now this generalized metric, because it is a subbundle on which the inner product is positive definite, and these two axes are actually isotropic, then it means that it has to look something like this. It's something that intersects transversally both of these things. I didn't say that, but like because of the signature of the inner product here, this V plus has to have necessarily the same dimension as the same rank as the dimension of M. So same rank as Tm. And all that means that this, you can see this V plus is a graph of a map. Let's say E, where E is a map that goes from T to T star M. Or alternatively, you can say that this is a section of T star M, tensor T star M. So it's a tensor with two lower indices, if you want, and you can split it in the symmetric and skew symmetric part. So the symmetric part will be some G, and the skew symmetric part will be some B. And now going back to this choice that we made at the beginning, so we chose this isotropic splitting. So if you take a different isotropic splitting, then what will change is that this B will be shifted by that two form. And so it's easy to see that actually there exists precisely one splitting. So there exists precisely one isotropic splitting. Such that this E will be symmetric, so there will be no B. Such that E is actually in the second symmetric power of this thing. And I can do it globally, so I don't have to talk about points. I can say that this was a global thing. And so this since it's symmetric, then that basically gives you the metric. So that's how you get this G here, and the H will be the three form that will correspond to that splitting. So this is how you get this pair. So G will be the graph of this generalized metric, and H will be the splitting H will be the three form corresponding to the splitting in which generalized metric is just a graph of something symmetric. And there are different ways to say this, but okay, let's just stick to this one. Anyway,
one comment that to make this one-to-one, you need to quotient by automorphisms the generalized metrics, otherwise it's not true. For this to be a one-to-one correspondence, you need to take generalized metrics up to automorphism of the product. This means that you're quotienting by all the closed two forms.
Really? Do you need to do that?
I mean, a generalized metric for sure determines G and H, but it has more information. It has the information of the isotropic splitting. It's just a small.
Okay.
So to make it one-to-one, yes, you need to take generalized metrics up to automorphism, and then
I see. Okay. Thanks. I didn't think of it that way. Okay, thanks. Yeah. Okay. Yeah. Now maybe a little bit more physics remark. So now, okay, maybe let's make a new page. So now this exact Courant algebroid. Okay, so if exact Courant algebroid together with the generalized metric, which will produce some pair G and H. So this is precisely the data that you need to have in order to define a string sigma model. So this is a data for what is called a sigma model. So more precisely, what this means is that, so suppose that I have such a data. So I have some manifold M, and on it I have this metric and three form. Now suppose that sigma is a Riemann surface. So that's like an additional piece of data. Riemann surface. Then you can consider map from maps, let's say F, that goes from sigma to this M. And for such maps, you can consider the following action functional, which is given by so basically you do this thing, and then you pull back the 3 form to, okay, so imagine that this sigma is actually the boundary of some 3 manifold y. So then, yeah, but this y is in a sense auxiliary. So like, what if, for instance, if you take variations of this action, then by Stokes' theorem, they will just, I mean, you can reduce this to just what is happening on the boundary. But yeah, I mean, so this is the way physicists usually write it. So this is what is called a sigma model. So it's a model described by this action where the field is given by maps from sigma to m. And this particular model is used in the study of, let's say, strings. So a bosonic string in the simplest case. So for us to make a connection with what was happening before, it basically means that the exact Courant algebroids together with generalized metrics provide some sort of natural framework for this. So at this stage, it's maybe not that persuasive because I didn't do anything with it, but like what I claim is that this really is a natural framework to work with such things, and this I hope will be gradually clear from what I want to say next, from some other properties that are related to strings. But before going into that, let me talk about the second piece of data that I wanted to put on the Courant algebra, and that's a divergence operator. So divergence operators. Divergence operators. So for this one, can go to works of Alexei Avenshu or Mario. So what this thing is, so let me say a definition. So again, suppose that you fix the Courant algebroid, and now a divergence operator is a map, should be not so surprisingly called div, that goes from sections of the Courant algebroid to functions on the base, satisfying one condition, such that if you take divergence of a section and then you multiply it by a function, then this you can relate to this expression when the function is taken out, but you have to have a correction term similar to that axiom in Courant algebroid. And this thing will have the form rho of u acting on f. So maybe let me, okay, so first consequence of this definition is that that divergences actually form an affine space. So divergences form an affine space over sections of E star, or actually you can erase the star because we know that E star and E are isomorphic. You can relate them using the inner product. So what does this mean? It's just that if you take two divergences and two divergence operators and you take the difference, then this term will drop out, and they will become C infinity linear. So there will be sections of some bundle, and that bundle is just E. So in other words, what I'm saying is that if you take two divergences, so if you have divergence, let's say divergence prime of u minus divergence of u, then this thing is given by taking inner product with some E, where E is a section of E. And I mean, for all u, so basically this thing, you can erase the u. This follows from this condition because this term drops out. Okay, the second remark would be related to the name. And because the more, well, I guess the main class of examples of such divergences comes from volume forms or densities on the base. So suppose that mu is a so take mu a density on M. You can think of it as, like, if everything is oriented, you can just take a volume form. So for such mu, you can define a specific divergence. Let me call it divergence subscript mu. And this thing will be defined by, let's say, if I insert A, then this thing is defined as I take the lead derivative of the density, and then I take the inverse of that. Yeah, so yeah. Right, and you can check that this satisfies this above property. So this is kind of an important class of densities, sorry, of divergences on the current algebra. And yeah, probably should have said non, I mean, okay, everywhere non-zero. Yeah, so that you can divide. Okay, are there any questions? So since I don't see people because I minimalized you, I don't know if people are still here, but I assume they are. Okay, very good. Okay, so now one thing you can do with divergences is that to every divergence you can associate an infinitesimal diffeomorphism of the or infinitesimal automorphism of the current algebra. So let me tell you how that works. So suppose that take div a divergence and take some mu. So this is maybe too complicated. So if I give you a divergence and a mu, then what I can do, I can take this mu and make a divergence out of it. So I can take this div mu, and I can look at the difference of these two. Sorry, of this div and div mu. And as before, this thing will be given by inner product with some e. Now the claim is that this is what's called the lemma. Claim is that if you take the bracketing with this section E is actually independent of mu. So this operation, when you see this as an operation on sections of current algebra, so this is actually independent of mu. It's independent of mu. So proof of that is kind of nice, although maybe not very straightforward. So the first thing that you have to notice is that if you take a divergence coming from this density, then it has some special form that you can show that this is basically some consequence of like how lead derivative works. So you can show that this thing, and let's check, acting on divergence will be plus acting on divergence mu of A. So this thing is 0. So this is a straightforward thing to do. Just like if you just substitute into this thing, basically the only yeah. So it's almost immediate. It's just they have to be careful because in this term we will take a derivative of this bit, and in this term we will also take a derivative of this bit. But these two guys they cancel, and basically what happens then is that you can take this prefactor out, and then you just get the usual formula, and you see that 0. So this is a straightforward verification. But now what this implies is that if you take the same thing but with this div, let me cheat and copy this thing. So if I now do the same thing but with this div, oops. Then if I substitute this thing, so if I instead of div I write div mu plus inner product with e, then the terms which will contain div mu, they will drop out because of this equation above, and what is left will be only this stuff with E. So writing it down, you get this one, and then here you get rho of A on E with B, and here you get rho of B, E with A. So right, and now you can use the axioms of Courant algebra. So for instance, from these two guys, you see that this is the same as, you know, like using the axiom for what this thing is. So you can acting with A on inner product is the same as acting on E plus acting on B. So acting on B is here, and what is left is the other term. So minus acting with A on E, comma B. So that's the sum of these two terms. And then if you rewrite this term a little bit, so if you write this guy as, you know, let's say D of EA, you know, like as a pairing. So this is a one form, and then you act with it on a, sorry, you contract this one form with this vector field rho B. Okay, this is maybe stupidly said, but you can write this thing as rho of transpose of D of EA, and then inner product with B. So this here, both these operations, they are the inner products on the Courant algebra. And now if you look at the two terms, then you can again see that if you use this symmetry axiom for Courant algebra, then you get that this is basically EA, comma B. And that's it. That's all. And then you see here that and these A and B, they are arbitrary. So this is true for any A and B. And so from that you see that because the original expression here didn't involve the mu, then also this end expression doesn't involve mu. So it's independent because these two things can be arbitrary. So yeah, that's it. So in this way you can associate. So the E is not, well, the E depends very much on mu, but the bracket with E, it doesn't. So in particular, if if this original divergence was actually coming from a density, then you can take mu to be that density, and then you get that E is 0, and that the associated automorphism is then 0. Okay, yeah. So yeah, that was one proof that I wanted to do fully. Maybe the only one. Okay, and now a little bit about compatibility of these two structures. So we talked about what a generalized metric is. So it was some subbundle, and we know what the divergence operator is. So now a natural question is like if there is a condition that makes these two compatible. So in that one we can following definition. So we say that the divergence is compatible with generalized metric with B plus if this automorphism here preserves this B plus. What does this mean? It means that if I take U, which is a section of V plus, and this is again a section of V plus. So this automorphism gives us a nice way to think about this definition. You can also write it explicitly what it means, but I think this is more illuminating. And so one example of this thing will be the following one. So suppose that so okay, actually the simplest example is to take any divergence which comes from a density is compatible with any V plus. So this is compatible with any V plus, simply because, as was said above, if I take this divergence generated by this density, then the associated automorphism is this bracketing here is 0 because I can take E to be 0, and that thing will automatically preserve V plus. But more generally, more generalized, there is more possibilities. And so one particularly nice, interesting thing happens when you take an exact Courant algebroid. Suppose that we have an exact Courant algebroid with a generalized metric. So now as I discussed above, if we have a generalized metric on a Courant on an exact Courant algebroid, then we get a preferred splitting. So this thing means that we will have we can identify this exact Courant algebroid with T plus T star M, and there will be some concrete tree form associated to it. And now you can ask, what are the possible compatible divergences? So first of all, if you have such a setup, then any divergence, if you have such a setup, there is a natural, there is a canonical divergence, and that one is given by the metric density. So if you have a metric, then you can have the metric volume form or metric density, and that will give you a natural divergence. And so because the divergences form a affine space, then any divergence will be actually of this form plus some E, plus some section of the Courant algebra. But in our case, E is actually directly this thing. So I can put X plus alpha here. So the possible divergences will be parameterized by a pair of a vector field and a one form. And now the claim is that such a thing, so this thing is compatible. Let's say div is compatible with V plus if and only if this vector field here X is a killing form. Sorry, is a killing vector field for G. So this V plus produces some G and some tree form H. So this is one condition. And the second condition is that if you take the D of this alpha, then it's the same as if you contract H with X. And the reason why I'm saying this is that this thing relates to what some people call generalized supergravity setup. So there is one particular case which corresponds to the usual supergravity setup, and so if X is actually 0 and alpha is exact, so if X is 0, then the second condition just says that alpha is closed. So if it's in fact exact, so if it's D of some field phi, then this field phi, this function, this is what physicists interpret as a dilaton field. And this X and alpha is something that some people would call a generalized dilaton. So again, let me use, before I use the red color to make a connection with physics, let me use that again. So let's say generalized string background. That's like the setup in which string can move. It will be normally parameterized by so you have some underlying, so you have some Riemann manifold, so you have some G, you have this tree form H, and then you have well, okay, if I didn't put generalized, then usually string theorists don't think about G, H, and phi, which we know that you can encode those things inside a exact Courant algebroid together with some B plus and together with some very specific dilaton, namely the one that comes from this construction with these conditions. But the point I want to make is that there is a more general story which is called generalized. I don't know if I can call generalized string background, or definitely the corresponding supergravity is called generalized supergravity or modified supergravity. So there is a more general story of this thing, where you have, instead of this phi, you really get this thing here. So this X and alpha. Yeah, I can make some more remarks on how this thing came to be, but if anyone is interested, you can ask me. So this thing in our setup, this would correspond to exact current algebroid with V plus and with a divergence that comes that is compatible with V plus, so compatible divergence. Actually, in this particular case, you can see that if this is true, then actually you can easily see. So if there is no x and this thing is exact, you can see that actually you can merge these two terms together, and you can say that this div is actually a div with respect to a volume form, and the volume form being e to the phi. This is the metric volume form. So yeah, maybe I should put it more to the right.
Is there a reference for this thing you call generalized stream background?
Mm-hmm. Yes. So yeah. Sorry, just a second. So if I call this mu, is basically the claim I'm making is that if you have exact current algebra with V plus and with a divergence which comes from a volume form, then this thing induces a dilaton field simply by taking the quotient of that volume form with the metric volume form and then logarithm or something. And so to answer Mario's question, so this is this generalized supergravity. Generalized supergravity. This thing was studied by where did I put it? Zeitlin and Wolf. I don't remember the archive number, but we definitely we cite them in the article. So and basically the origin of this thing is that so when you're studying string theory, there's several approaches how to do that, and one of them is that you have a sigma model like the one we have above, and yeah, and then you do something with it. You quantize it. You take well, there's a whole business around it, but there's a different thing that comes from taking a so-called target space or target space approach, whatever. It just means that you don't deal with any surfaces, any Riemann surfaces. You directly deal with the space-time, and you have some fields living there. So in this case, it will be the metric, basically these things, and they are governed by some action, which would be for superstrings, this would be the supergravity action. And there is a connection between these two things. So for instance, if you have this sigma model approach where you have really like some surface embedded in your space-time, and then you try to quantize it, then there is some constraints on this model. So this model, in order for it to be meaningful, it has to satisfy some constraints. And these are constraints on this target data. And what you can show is that these constraints basically correspond to a solution of the supergravity equations of motion. So you have some. So in order for the sigma model to be meaningful, the string has to move in a background which is given by some field which satisfy equations of motion. And yeah, hopefully I'm not messing this up. And so so I think the claim is as follows. So people notice that if you're now doing superstring theory, and if you take background, if you find a solution to the supergravity equations of motion, and then you are studying superstring which moves in this background, then the action of the superstring, it will possess some specific symmetry which is called kappa symmetry. So it will just have some sort of, it's some type of supersymmetric thing. It's like an odd transformation on the field, something. And this kappa symmetry is kind of important for people. And then people conjecture that actually it's if and only if you have a string sigma model which has this kappa symmetry, it means that the target, this space-time, it has to satisfy the supergravity equations of motion. But then it was proven wrong by these people. They showed that actually you can have the fact that the action, the sigma model, the string sigma model has this kappa symmetry, it only implies some weaker version of these equations. So it implies these generalized string background equations. But it's a strange thing, because if you take like a generic spacetime, then it will have no killing vector fields, I guess. So then X you can say that X is 0 based on some like more, what am I saying? Yeah, maybe disregard what I just said, but yeah, so it's kind of, yeah. I don't know what I wanted to say, but yeah, so it's a small upgrade of this original story, and then there is an argument whether this thing is just like a mathematical fact, or if it has any deeper significance, because some people say that this well, I guess most people say that this generalized string background, it's not really a string background, because you don't really, because the string moving there, because something goes wrong there. So like what is really physically important is this other thing. But what I find interesting is that like this Courant algebra approach, it incidentally seems to recover precisely this thing. I mean, it recovers both, but like in a sense, this divergence approach, it kind of naturally encodes these two guys. Yeah.
If I may add something about this discussion,
please.
I would say that these generalized supergravity equations, I think, if I'm not mistaken, that people believe they are not supersymmetricizable. So even if we call them supergravity equations or generalized supergravity equations, that doesn't mean that they are the bosonic part of a truly supersymmetric theory. So
really?
They are a generalization, of course, but in order to have a supersymmetric theory, you have constraints, and actually all local supergravities, at least in the engaged case, they are believed to be fully classified, and they are not. So it is hard for these new equations to actually correspond to a true supergravity equation. And I think they are derived from a kappa symmetry argument, as you were saying, but this is not the same as supersymmetry.
Right.
So
yes, sorry.
This quick comment. So
thank you.
I don't know the status of these generalized supergravity equations, but I think it's believed that they are not supersymmetricizable in the generic form in which this vector field that they introduce is arbitrary. This X you're calling. So at the end of the day, locally it's very hard to deviate from the local supergravity equations that we know, because they are essentially unique in this dimension.
I see. Thank you.
Sure.
Yeah, maybe one thing that just came to my mind is like the reason some people are interested in this generalized story is that and that was kind of, I guess, the origin of the work of these two people, is that people discovered that there was a solution. So when they were trying to deform some string models in a way that they would preserve integrability of the model, then there's something called eta deformations. So I think the original one was ADS 5 process 5. So they noticed that you can introduce some sort of deformation into this for this data, for this background, and it will still keep some nice properties. It will lose the property of being a proper string background apparently, but it will still be integrable. And then they noticed that this was actually a counterexample to that thing, because the string moving on such a thing, but the action would still be kappa symmetric, but it would not correspond to like a proper supergravity. So what I'm saying is that people interested in integrability, they are still interested in these generalized things. That's my understanding. Of course, they are probably more interested.
I'm sure this is fully justified and sure. But the construction of supergravity theories is a different problem. It has nothing to do a priori with a string moving in a space-time. It's just a different problem. The only thing is that a posteriori they can be related in some situations, but in general, construction of supergravity theories is a different problem from studying the dynamics of a spring moving in some target space.
Okay, okay, I see.
Just yeah.
Thank you. Right. Okay, very good. So yeah, this was the this was part number 1, but this was supposed to be the longest part anyway. So I think it's probably so now that we talked about what the generalized metric and divergence operators are, then now we can talk about generalized Ricci tensor. So first I should put some references. So second part, generalized Ricci. So I should say that so the work that we did with Pavel, that was, I mean, there was a great deal of work that was done before us, particularly by Mario, and let me say maybe the history, and probably I will still omit some people, for which I apologize. So there was a work by Marco Gualtieri, and there was a physicsy paper, quite influential one by Coimbra, Strickland, Constable, and Waldram. Here there is Mario. And there is the Prague group, Jurcho Vysoky. Oh yeah, yes, sorry, it's probably not going to be chronological, so I apologize for that. There's also also Jeff was working in this. So I like so the things that I want to present, they in a sense they stand on the theory and observations of all these people. Yeah, and then okay, with Pablo we also had some previous work on this. So basically, generalized Ricci tensor is an object that is supposed to mimic the ordinary Ricci tensor for an ordinary metric, but where now everything is generalized. And the reason why that is interesting physically is that it corresponds to some renormalization group flows of these models, or incidentally, it also corresponds to the or the critical point of that corresponds to solutions to supergravity equations of motion. Yeah, but in any case, so the problem in defining this object is that it turns out that, so if you want to mimic the classical construction, and you take a metric and then you take a Levi-Civita connection and then you construct the curvature tensors and in particular the Ricci tensor, so this thing fails a little bit because you can show that there is a problem with Levi-Civita connections. For one thing, they are not unique, and it turns out that this resulting tensor does depend a little bit on the choice of this connection. But then I think it was Mario who realized that actually the only important part of that connection that contributes is given by its trace, which should correspond to this divergence operator. So basically, the upshot of all of this is that the generalized Ricci tensor, which is like ideally it would be something defined for a generalized metric, but it's actually not. So you need a little bit of more data, and that data you can phrase it either as a connection or as a trivialization or something. But in our approach with Pavel, we take the divergence. So this is basically the type of data that enters, and that will precisely correspond to the string approach where you have a metric the H field and the dilaton. And yeah, I guess the novelty in what we did was that we kind of wrote down the expression that was equal to the other expressions, but it was written in a different way that made it natural to. It kind of made some properties natural that we then use to prove some statements about Poisson-Litty duality, which I will talk about later. But maybe to draw some picture. So suppose that you have a Courant algebroid. So let's say Courant algebroid E. And now if you look at the space of all possible, so let's associate to it the space curly M, which will be the space of generalized metrics. So this will be some huge infinite dimensional space, at least to have some picture in mind. And the point of that is given by subbundle V plus in E. And now this generalized Ricci tensor, it is supposed to be a vector field on this manifold. That's what it is. So this is the generalized Ricci. But as it turns out, you cannot just you need to have some extra piece of data, namely the divergence. So basically, if I want to say that there is a vector field there, and I need to say that it's generalized Ricci for some divergence. And then at every given point, there is a V plus, and I can write it down what it means. So if I want to maybe be more specific, then so I want to define what this thing is. And I'm saying it's a vector field. So let me talk about what is a vector on this space. So if you have this moduli space, and you are sitting at a particular point given by a generalized metric, then the tangent space to that can be identified with the space of like infinitesimal deformations of the subbundle, and that is an easy way to do. I mean, that's the same as vector bundle maps from V plus to its complement, so to V minus. Because if you have let's say, if you have V plus and V minus being just the orthogonal complement to that. Now, if you deform this slightly, then this small deformation will be transverse with V minus. I mean, it will have zero intersection with V minus, and hence you can see it as a graph of a map from V plus to V minus. So this is a graph of some map, I don't know, lambda from V plus to V minus. And hence, yeah, and hence, so the infinitesimal deformations, you can identify them with such homes, with such maps. But now, since we said that there is an inner product on Courant algebroid, and on V plus it's actually positive definite, here it's negative definite. So in particular, there is an inner product on these subbundles, then you can identify V plus with V plus dual and V minus with V minus dual, and in particular, you can say that this is the same as a map from V plus tensor V minus to R. So this is a little cramped. And it is this last incarnation that I will use in the definition. So I will now describe a natural object sitting in here, and that will be the Ricci tensor. So in order to do that, so suppose that you have two sections. Let's say one. Let me use the subscript to just so that we remember that this is a section of V plus, and V minus will be a section of V minus. Okay, so this is just a part of the name, just to keep us reminded that it's section of V plus V minus. And now consider the following weird expression. So you take the divergence. Okay, so as before, so suppose that you have a Courant algebroid. You have a generalized metric, and you have a divergence. So this is the data needed to define such an object. So now, having such data and having these two sections, then what you can do, you can form the following thing. So you take the bracket of these two things, and then the result that you get, you project it down to V plus. So this thing means that I take the bracket and then I take the projection onto V plus with respect to V minus. So orthogonal projection or onto V plus. And then I take, so I admit that this is a weird and unnatural looking expression at first sight, also at the second sight. Yeah, so then you subtract this thing, so you take the divergence of that, and then you get a function, and then you act with this thing. And then you take one last bit of ugliness. So you take trace of the following operator, take this thing, project it to this, and then project this thing, and project it to plus. So consider for a moment this weirdly looking expression. I will slightly justify it in a second, like why this expression precisely. But So my claim is that this expression has some interesting properties. So first of all, it is actually linear, like function linear, C infinity linear in both slots, in both A and B. So, okay, so that's what we call the proposition. So that thing is actually C infinity M bilinear. So hence it defines a section, hence that expression without these two things, it defines a section of elements of V plus tensor V minus say star dual. And that will be the Ricci tensor. So now I define the Ricci tensor to be generalized Ricci for a given V plus and divergence acting on A plus and B minus. I define it to be that thing. Okay, so this is probably the weirdest possible way to define Ricci, but it has some great advantages. So first advantage is that it doesn't use a connection. So it only uses the data that really enters in it, in a sense. So it only uses V plus and it only uses the divergence, and those two things are related to these physical fields that you want in the supergravity.
Sorry, Friedrich, here you're not assuming E is exact, is it right?
Say again, sorry.
You're not assuming E is exact.
Yeah, precisely. I'm not. Yeah. This is a general Courant algebra. So this is a general. Yeah, that's actually the point. So that will be the point of the second, like next time, that when you want to talk about Poisson-Litty duality, which is some sort of equivalence of some two theories, then the easiest and most natural way to phrase that thing is to phrase it in terms of pullbacks of some Courant algebras. And the advantage here is that this thing is natural with respect to pullbacks, because all these operations that are involved in this definition, they behave nicely with respect to pullbacks. So it's easy to see that if you pull back generalized metric and you insert pullback sections, it's the same as if you would, like if you would take the original one, insert the original one, and then pull it back. So it's natural with respect to pullbacks. And this itself immediately proves that it's compatible with like supergravity equations, that Poisson-Litty duality is compatible with supergravity equations of motion, things like this. So there's like no calculation needed. So that's the advantage of this. While if you would have connections, then it's slightly more complicated, because you need to pull back connections, and you need to study of like when it's even non-trivial to answer like when do these would be Levi-Civita connections, when they exist and stuff like this. So this thing kind of avoids all these problems. So this is for general Courant algebra. Yes, that's right. So as I said, one property is that it is well defined as a section as a map, as a vector bounded map. So it's C infinity linear in both slots. The other property, which is perhaps even more important, is the one that justifies the name. So if you take, in a special case, when you take exact Courant algebra with a generalized metric, so we know that this thing corresponds. This thing gives rise to some G and H, and in particular, because we have a metric, we can take the metric volume form, the metric density, and we can take the divergence with respect to that. So there is a natural divergence associated to that thing. In this case, we don't need any more data. And in this case, you can show that actually this generalized Ricci tensor for this V plus and this divergence with respect to this metric volume form, if you put A plus and B minus, it recovers the usual Ricci tensor, calculated now for a metric connection with a torsion given by H. And and here you get A plus and B minus acted upon by the anchor map. So this is why, and this is the thing that appears in the string. If you do the beta function, the one loop beta function, then this is the expression that appears there. And yeah, basically the reason for to prove, I mean, so to prove this equality, then what you need to do is that you, well, yeah, there is, I guess, many ways to prove it, but like one way to prove it is to realize that, and that in some ways slightly can be used as a suggestion for why this expression, and that's the following claim, that if you take nabla to be any connection on TM, I guess it doesn't even need to be metric compatible. Well, yeah, I think it doesn't. Then you can show that the Ricci tensor for that thing is given by an expression which looks very much like this. So there will be nabla y of x minus y acting on, these are two vector fields, x and y. So this is an expression discovered, I think, by Paolo. So here, div nabla is the trace of the connection. Div nabla acting on x is the trace of nabla x. And this thing here should be the connection with opposite torsion. Some connection with opposite torsion, if that makes sense. So apparently you can reshuffle the ordinary Ricci tensor, again, this sort of weird thing, and then to make connection with the brackets here, then you use this well-known thing that if you take something in V minus, take a bracket with something in V plus, and then project it to V plus, and this is the same as taking this. I think this is the bismuth connection, if I remember the nomenclature correctly. And similar with the other way around. Project into V minus, this is the same as this other connection with the opposite torsion. Rho V plus, rho V minus. Yeah, and I think putting these two things together, it should directly give this thing, if I remember correctly, probably. So this, yeah, okay, yeah, so that would be that's what is required in this calculation. Yeah, so we know that it's well defined. We know that it's linear. We know that it recovers the ordinary Ricci tensor. One thing that maybe that you can address is also how much does it depend on the divergence? So again, consider the more general setup, and suppose that you take instead of divergence, you take the divergence prime, which will differ from divergence by some inner product with some section E. And the claim is that the generalized Ricci tensor for this div prime will differ from the original one, div, only by minus projecting this, by taking this E, taking its V plus part, so projecting it to V plus, and then taking something like this. So this expression on the right hand side, so here I mean there is these two slots everywhere. So this thing basically means that if you change the divergence, the general this Ricci, it only changes by an inner automorphism. So by there's just like some bracket of some section involved there. So from this you can deduce that basically strictly speaking, it does depend on the divergence, but changing the divergence only changes it only amounts to like applying some automorphism on that thing. So they are in a sense equivalent. So if you want, you can just say that this really just does depend on V plus, but yeah, but it's not really up to some automorphism. It does. Yeah, and then to make a connection with physics, just let me repeat what I said before, is that this generalized Ricci flow, it corresponds to one loop, meaning to the lowest order of approximation, one loop RG flow of the sigma model given by this G and H. So this is for an exact current algebra. So if you have exact current algebra, the Ricci flow corresponds to RG flow of sigma model given by G and H. Actually, I can erase this because there is a recent work by Pavel, I think, with Jan Pullman and Donald Humans, where they showed that you can also recover this more general Ricci, meaning for non-exact current algebras, as a RG flow of a suitable what is called current sigma model. So there is a natural extension of this story, basically of this action of this story. There's an extension of this story to like more general setup. And you can recover this generalized Ricci there as an RG flow. So it's kind of interesting. Yeah. Okay. So this is the Ricci tensor. I don't know if that was comprehensible.
I mean, just I mean, I like this description you wrote in blue. I guess gives some motivation for why you might. I mean, I don't know. Somehow it's sort of indisputably capturing something meaningful. I guess this definition. I just wonder. I don't know if there's any other motivation for the definition other than like what you wrote in blue there, or like how you come up with this in the first place. I
yeah,
guess,
that's a good question. So this was. I think I really forgot how this was, but I think this was basically just trying to. It was some sort of a fusion of. One way was to kind of just like play with the ordinary definition, with the usual definition using connections, and make it, and just transform it in a way that it will only use the traces of those connections.
I see.
And yeah, I think that's how it's. Yeah, I don't really remember, but it was some probably fusion of that and of this formula. But I don't remember if we knew this formula before or if it was just like afterwards. Yeah, I don't quite remember, but what is, yeah, but I mean, once so actually the precise form of that expression is not important. Like what is really important is that it is natural with respect to pullbacks. Sure. And that it is linear and that it recovers the Ricci tensor. So that's
sure. Yeah. Sure.
So sometimes when I'm giving talks about this, I just say that there is a way to define this, and like it has these properties, but it's not that illuminating. I mean, it's not terribly complicated, but it's yeah.
Sure. No, thank you. That's helpful.
So yeah, so I see that I'm getting to the end. So maybe I can start talking about the Laplacian, and let's see how far we go, and then I can stop.
Okay.
Okay, so Laplacian and scalar curvature. And so this is a little bizarre thing that we don't really know how to. I mean, the thing I will write is correct and everything, but there is a natural question of like how one can arrive there in a more natural way. So let me tell you what I mean is that, so suppose that you take a current algebra, arbitrary current algebra, not necessarily exact, and you take a generalized metric. Now the claim I want to make in this section is that you can associate a natural operator just given by these two data, and that is a sort of Laplace operator. So let's call it Laplace with a subscript v plus. And this is an operator that acts on half densities on M, on the base manifold. And And now I will write the expression, but it will be probably even less illuminating than this one. But as opposed to this expression, this thing will even require to have like some like the problem is that we don't know how to write it without choosing some like trivialization of the bundle or something. But it's clear that it has to have some description, but we just don't know what it is. So let me write down what this thing, the definition of that. Let me first write it and then say what the things are. This. There is also a way to draw to do this in terms of pictures, which I am particularly fond of. But in order to introduce the pictures, I think that's maybe not optimal for a presentation. So here, what I suppose that we do is that here we take let's say orange. So this thing has a decomposition into. There is a subbundle and its own or in its complement. And now suppose that we pick coordinates. Sorry, we pick a frame, like we pick a locally, like around above some neighborhood of the base manifold. We pick some local frame, let's say, and I mean a frame which will be adapted to this. So meaning that we take a frame EA of V plus, and we take a frame of V minus, which I will call. It's probably a terrible notation, but let me call it a bar. Here, this does not imply that A and A bar like have the same. That for every A there is an A bar. It's really like this labeled some two different index sets. Yeah. So suppose that we take this thing in such a way, moreover, that if you take inner product of any of these things, so instead, so for instance, this ones or this ones. The cross ones will be 0 because those two are orthogonal. So we want that these things are constant. If they are constant, then this implies that if you take their brackets and then a contraction, then this thing will be completely skew symmetric. And it is this thing that I define to be the C. So C, A, B, C, or. But let me put alpha, beta, gamma to say that I mean you can take any A or A bars here. So totally I will call this A alpha, E alpha. So this I define to be C beta gamma delta. C alpha beta gamma. Yes, so these are the C's that enter here. So these are the structure functions of the courant algebra. These are the Lie derivatives acting on half densities. And indices up and down, they are just lowered and raised using the inner product on the courant algebra pairing. So this is the expression. I will put it maybe with like a large red. So this is like an open question that we haven't been able to answer yet. Like how to define this. Like what is a better definition? And so, but this is the right object. Like we know that the object is the right one because it has the properties. It has the following properties. So first of all, let's call it the proposition. So this delta V plus is independent of the choice of this trivialization. Is independent of this trivialization. That's one property. Secondly, if you take bullet number 1, bullet number 2, if you take exact courant algebra again, and you take V plus, which translates to this pair of a metric and 3 form, then you can show that actually. Then we know explicit. Then this thing simplifies. So if you act on a general half density, so general half density will be given by some reference half density. So we take the the metric density, and we take the square root of that. So this is the A half density, and we multiply it by a function. So this gives the general half density. This thing is given by, okay, it has to be half density again. And the stuff which we get here is the ordinary Laplace operator, the Riemannian one, minus 1/2 of the scalar curvature in the usual way, and the norm of H squared, and this thing acting on F. So right. So in particular, having defined this thing, we can define a action functional. Let's call it S of for E being current algebra E. So this is an action functional which depends on the generalized metric and depends on a half density. So let me call, no, this is a half density. And this thing, you can define it to be minus 1/2, remember correctly, minus 1/2 of sigma Laplace sigma. So you act with the Laplace on sigma, get a half density multiplied by sigma, you get a density, and then you integrate it. And then this expression basically says that if you break it down, then for an exact current algebra, if you take V plus, and if you now take so if you take sigma to be this metric one, but multiplied by this dilaton, so I guess I should probably multiply it by e to some power of phi. This is how you encode the dilaton. Maybe there is plus minus. Sorry, there is maybe a factor here. I don't remember. Yeah, this gives precisely the string effective action. So this is 1/4 of R minus 1/8 H squared plus norm of d phi. Sorry, there is a mistake. I don't know what is happening here. Okay, times the metric volume form. Oh yes, and the dilaton. Sorry, so this thing is multiplied by and then so this is the string effective action, and right. And okay, maybe just to say that briefly. So now if
are you using some unusual convention for what is the norm of the square of H? Just because typically you have 1/12 norm of H.
Maybe. Wait. So this thing here has 1/6 6ijk. So yeah, I guess it's maybe an unusual convention, but I'm pretty sure it should be the standard one. I mean, the overall. Maybe there is some overall factors that I don't. Would it work if I would put it like this? If I would take 1/4 out, 1/4 out.
Yeah, that way.
Okay. Right. Yeah. So maybe to link this thing with the Ricci tensor. So if you have to suppose that M is compact, and suppose that sigma is a non-vanishing, everywhere non-zero half density. So I don't know. Let me write it like this. It's not. Sorry, no, that's not what it means. Sorry, sigma is everywhere non-zero fixed half density. If you have such a thing, then on the moduli space of all possible generalized metrics, there is a metric. So this becomes Riemannian. So it has a metric. Simply by, if you look back at what this moduli space was, then sorry, where was this? Yeah, so the tangent space was either could be identified with this thing, or alternatively, this is the same as sections of B plus star, or using the metric. So you have two sections. You can just take you can just pair you can just pair them, and then you can integrate over the manifold, and that gives you a number. So you have two deformations. So if you have phi 1 and phi 2 in deformations of this thing, which is the same as sections of B plus, then there will be there's something happening with my tablet. Sorry for that. So what I can do, I can pair them, meaning I take inner product in the first bit and in the second one, and then I can take the integral over m, and maybe with a minus because this thing is negative thing. So this thing gives a number. So in this way, I get a metric on this infinite dimensional space. And now the claim is that this action functional here for a fixed sigma, this gives a function whose gradient is the generalized Ricci tensor. So generalized Ricci for, let's say, for a divergence given by this sigma. So sigma induces a volume form, but it induces a density if I take a square of it, because it's a half density. I can take the divergence, and if I take generalized Ricci with that divergence, then this thing will be, there's a minus gradient of this SE for this sigma. So it's a gradient flow for this weird function. Yeah, or maybe I can say that, okay, maybe more concretely. So if I take, that's going to be the same thing, but so if I take phi in here, so in tangent space, and I use this phi to deform slightly the generalized metric, and I look at the variation. So I vary the action function now. This sigma. Then this thing will be this thing. Contracted with phi, so let's say contracted with phi, and then sigma squared. Okay, sorry. This inner product here, it needs to involve some density. So this is how you get the density enters.
It's the neutral inner product there.
This one, yeah, this one is this thing.
And also in the, yeah, oh, okay, yeah.
Right, so yeah, that's basically all I wanted to say. Maybe I can make one more line, just that because I promised a scalar curvature. So now, if you take, you can define. If you take a generalized metric and you take so this is everywhere non-zero. Everywhere non-zero half density, then you can define this thing to be the sigma minus 1 sigma. So yeah, so you just act on sigma and then you remove the sigma, so you get a function. So this is a function on the base. But in a sense, this Laplacian seems to be more fundamental in a sense, because I mean you use it to construct the curvature in this way, and it has these nice properties with this action functional. Maybe I should highlight this bit. Yeah, but okay. So just to close the entire thing, just I would say an open question in this is that what is a coordinate independent, or what is a better definition of this nabla? So what of this delta that doesn't use this weird decomposition, which would make it immediate that it's independent of any choices. So it should have such an explanation, but we don't know what it is. So that's yeah. Yeah, and with that I would probably end for today. And sorry for taking longer than I anticipated.
Oh, yeah, that's great. So let's thank Friedrich again. Thanks. And well, what motivation can you give for the definition other than capturing natural examples for the scalar curvature, or for this Laplacian in any case?
Yeah, I don't really. Okay. I think originally we discovered this expression. I think, if I remember correctly, we discovered this by looking at the example of the Lie algebra. So if you take a current algebra over a point where it's just quadratic Lie algebra, then all this becomes very simple. And then, right, yeah, I think that was the origin of that story, because so actually when we're working in a Lie algebra setup, then it's kind of useful to use diagrams so that you don't use any indices or anything. So for instance, generalized Ricci tensor for a Lie algebra. So if you take E to be just Lie algebra with some inner product, and you take the zero divergence, because here it makes sense to talk about the zero divergence, because that will satisfy the axiom. So here you can take divergence to be zero. So now this Ricci with this zero divergence, it will become something that we usually draw it like this. So it's a diagram which looks like this. It's basically, if I go back to the definition, because it's sorry, where was it? Here, no. Here, sorry. Yeah, I mean, if divergence is zero, then these two terms go away, and the only thing that you get is this trace thing here. So basically, that's graphically interpreted like this. So if you put this A plus and B minus, then that would correspond to something like this. Where what this thing means is that you take A plus, take some vector, let's say x, and take these two things. This trivalent vertex means that you take the inner product. So sorry, not the inner product. The bracket. You take the commutator of those two things. So the trivalent vertex corresponds to structure constants. So you take so if I would write this, then this just means that it's the product of these two, the bracket of these two things. But now what I do further with it, then I make a projection onto V minus, I think. So this thing here means that I take a projection onto V minus. Then I take a further bracket of that result with B minus. Then I take a projection onto V plus. And then I take a trace. And trace means that trace in X. So that means that I make a loop here. So that's how you get this diagram, and that's why it corresponds to that expression above, which was like a trace of a repeated commutator and projections. And yeah, probably it was unnecessary to draw it. Sorry, but then like we found using this Lie algebra example that actually you can see this as a gradient of a function, and the function is given by a similar diagram, which looks like this. And I think maybe it's 3 or something like this. I don't remember. So these nodes, they just signify projections, and then you get some expression like this. And this is precisely the meaning of these two terms in. Sorry, I'm lost in here. It means that you take two structure constants. For instance, this one, you take two structure constants, and then you contract all the indices, but only along the V plus directions. So that's the first diagram, and then you get the second term looks like this. Yeah, this was probably not necessary to draw. Sorry. I just wanted to say that, like in the Lie algebra case, it really boils down to some simple algebraic manipulation or some pictorial, and that's how we determine these two terms. And I guess then I think probably then Pavel guessed this first bit that looks kind of natural.
Huh. I mean,
Yeah.
is it? What's my question? Yeah, like, is there like an underlying Dirac operator or something? Should this be the square? Of the operator?
That's a perfect question. Yes. So yes. I mean, no. So the answer is no.
Okay.
But the answer is that's the weird thing, because it almost looks like a square of a Dirac operator. And yeah, that's what I want to talk about next, I guess, about this Dirac operator. So the thing is that as I wrote it here, this only depends on E and V plus. But actually, it's easy to see that you don't need to require this positive definiteness for V plus. It's enough to just assume that this V plus is a subbundle such that the induced thing is non-degenerate. So if you assume that this is just non-degenerate, it can have different signatures, Lorentzian signature, it can be whatever weird, but then most of the story that I wrote about, or actually all of it, carries over. There is just like at some point you have to insert some technical assumptions, but like it basically all goes through. In particular, this definition is also valid. And then what like a nice remark is that if you then make this more flexible definition, then you can take E itself to be a generalized metric, because the metric there is non-degenerate. And so you can calculate the Laplacian for that, and that gives the square of the Dirac operator with some constants, with some proportionality constants.
Oh, okay.
So there is so in that case it is related to the Dirac operator, but in the case when you don't take E but you take just a subbundle, then it almost looks like it is related also to something like that, but it's not. We cannot really make it work. It looks like there's two terms missing. You see, because you here you are summing over all three of them being in V plus. Then there is a sum where two indices are in V plus and the third one is in V minus, and then there is two more terms which are missing. Then you should also have some terms which have two like this, and then you have term which has all three of them.
Yeah, right.
Part. And this is just some like weird cut truncation where you just take these two terms, and for some reason it's well defined, and we don't really understand why, or I don't really understand why.
And so wait, sorry, if you, I wondered about that too. So if you somehow just like symmetrize the expression you have there involving the structure constants over the plus and minus bundles, what does it give for like an exact Courant algebra?
So I think it might be the same. Wait.
Like maybe the apparent asymmetry is not really there. It somehow is actually symmetric over plus and minus or something.
Yeah. So I think if you would write down the same thing with, if you would replace V plus with V minus, I think the whole thing would then differ from this expression by the square of the Dirac operator or something, which is constant for, which is zero for exact.
Well, okay, that's one thing. Well, yeah, so there's like the definition you have for V plus or V minus, but then there's also just this, I mean, it's very naive, but I like just looking at that expression involving the C's, yeah, like this sort of lack of symmetry between plus and minus is somehow, what does that mean to prefer the one over the other? Anyways, it's sort of unusual to me. But on the other hand, it does produce an interesting known example. So it must be meaningful, I guess.
Right. Yeah, I agree that it looks weird. Yes, that I totally agree. But I don't know.
I guess I don't really have a question. Yeah,
No, I totally agree with that.
And if I may ask something, this Dirac operator you were mentioning, on which spin or bundle does it act?
So that's a thing that I wanted to discuss next. So that's an operator that is associated to any Courant algebroid. it doesn't require any generalized metric. It's just a canonical operator, and it acts on spinor half densities. So these are spinors with respect to this Courant algebraic. So you see there's a bundle. So
what does that mean? Spinor with a
yeah. So this bundle. So the Courant algebra is in particular, it's a bundle with an inner product on fibers.
Mm-hmm. Yeah.
So you can form the Clifford bundle for that.
Yeah.
And then you take what do you do then? And then you study the representations of.
So you want to consider the bundle of irreducible Clifford modules over this Clifford of E.
Yes.
Okay.
Yes, that's right. Yeah, and for in the most important case, in the case when this is actually exact. So if this is exact, Courant algebroid, then you can, if you choose an identification with T plus T star, then this has a split signature. So the inner product here has like a split signature, and the corresponding spinors will be just differential forms mostly. So actually what is really true is that the spinor half density.
Yeah, my question will be about the case in which this is not exact, because this case is actually the most convenient one in that respect. But if you change the signature now, the type of bundles of irreducible Clifford modules change, and they are in general not associated to spin structures, but more general spinorial structures. And in that case, you pick up an extra term in the square of the Dirac operator, which is the curvature of the characteristic bundle of the spinorial structure associated to this type of spinorial bundles. And I've never seen such type of term arising in a generalized geometric context. So I was curious about this. So in more generality, when you have a bundle of irreducible or faithful modules over the bundle of Clifford algebras, you don't have a spinor structure. You have a spinorial Lipschitz structure, which is in general more general than a spin structure, and you have this extra bundle. So they are of the type spin, instead of being spin structures, meaning principal bundles with structure group spin, they have more general structure group of the type spin dot something. This something can be U1 and you have a spin C structure, but it can be something more general like SU2. And in those cases, morally speaking, essentially you have a connection on this SU2 bundle popping up everywhere. So when you compute the square of the Dirac operator, you also get this type of SU2 curvature. So I was wondering about the relation with between these type of extra curvature terms and this generalized geometry formulation. But if you're going to talk about this next time, I understood well, then I can wait.
That was the plan. But maybe I can say one thing. I probably doesn't answer anything, but it's like this, like so this generating Dirac operator. It's actually, it can be seen as an element of something that you can call it a differential operator with Clifford coefficients. So yeah, so it doesn't necessarily need to act on anything. Maybe it can be just defined as an operator. It's a, what is it, like a section of some. Yeah,
I thought you mentioned a Dirac operator. You were meaning a Dirac generating operator?
Yeah, sorry. Whenever I said Dirac operator, I meant this Dirac generating operator or generating Dirac operator. Sorry, I never know which.
Okay.
Can I ask something?
Yep.
Yeah. So for first one I think, so you said that somehow from these diagrams, you read that the variation of the scalar curvature is the Ricci somehow.
Yes, so sorry, the diagrams were not necessary to read that off. It's just that, like, I wanted to draw something, and for some reason I decided that this was the right moment to draw something. But yeah, I mean, yeah, but I kind of, actually working with diagrams was what made it very easy to do that. Yeah, the whole point of this blue thing was just to say that I think we discovered it first for this Lie algebra case, and then we just noticed that you can easily make it work everywhere, like for anything.
Yeah, I guess it's pretty closely related to what Jeff was saying. But so what happens if I formally change B plus and B minus in your definition of this operator delta B plus? So does it give the same answer, or is a different thing?
Yeah, that's a good question. Wait, how did this go? I mean, if I remember correctly, and I maybe don't remember correctly, but if you maybe if you put these two things together, yeah, I'm confused about this minus. No, sorry, maybe there was a plus sign actually. Sorry, it's a different. There was a. Oh, there was a relative plus sign. Okay, then it doesn't matter. Yeah, so then I think what happens, so there should be plus. I guess this is 1/6 and this is 1/2, 1/2. What I want to say, yeah. So if you would put the other stuff in, so you would symmetrize it. So you would put like minus plus, and the other one. Then then the other one. Then you get that this is just this thing. I mean just by which I mean they just contract structure constants together, which incidentally is just the square of the Dirac operator. So it's something that's not that interesting. It's something that's independent of V plus in particular. That's why it's not that interesting. This is just because if you have a because the projector onto V plus projector onto V minus gives the identity. I mean, you can decompose the identity as the two projectors, and that's how you get this thing.
And in relation to the way that Waldron, Strelian, Constable, and Coimbra define the generalized curvature, did you manage to relate your operator to these Dirac operators that they define, and the rough Laplacian and so on? So in their definition, you have one connection, which is, say you're working with B plus, and then you have the nab Laplace connection and the rough Laplacian of that. And then associated to B plus and a divergence, you also have a Dirac operator acting on spinors for
Right.
And the square of the Dirac operator minus the rough Laplacian is the generalized curvature. So
right.
I don't know did you see any relation with that?
Yeah, I think there was a relation. Let me remember. No, I don't remember. Yeah, I know what you mean, but I don't. Yeah, sorry, I don't remember, but I know. I mean, you've done some things on this, right?
Well, yeah, I just understood what they did, and there is also something on the book with Jeff about that. But I wanted to know if there is a clean relation between the two things, the two approaches to generalized calculus.
Yeah, yes, maybe. But I'm really sorry. At this moment, I think I forgot the details of that. But I remember the construction that you're saying. Like they have this, yeah, this generating this kind of these Dirac operators for these subbundles, like for V plus and V minus or something. Yeah, and then they take squares of that. No, but I really forgot. Sorry.
That's okay. It's a very nice talk. Maybe yeah, let's thank Friedrich again. I can at least stop the recording. So yeah, thanks again.
Thank you.